All right, folks, any moment. Yeah. All right, folks, are we all back? All right, folks. So today we are going to read two papers that you have hopefully read. And we are, guys, can somebody explain to me what is this paper saying? Anyone? Aditya.
This one is, that was the first one. So this one more about the adversarial examples, the same example which is listed. They are listed over here, the panda and given, and the small perturbations can cause those problems. They were listing about adding some small amount of noise in your data, which can cause those perturbations and then cause these problems in models.
Yeah, but why does it work? How does it work?
Kate? How does it work?
The main point I got in this paper was that they're saying it's a problem with the activation functions being too linear, and that they recommend a non-linear activation function like
to solve it. Yes,
that.
That's right. So that's a great point. So guys, this is one of the earlier papers. The adversarial attacks showed up in 2013. Many researchers, more or less at the same time, observed that you could attack a neural network and with impunity make it mislead it. Right? So you can have, for example, a panda get classified as a gibbon. Right? So people try to explain why it happens. And in this paper, like this particular method that is there, it's one of the simplest methods to confuse it. Now, this paper goes into a lot of explanations of why it happens, why adversarial attacks happen. Since then, since 2014, when I believe the first version of this paper came, to now, many years have gone by, a decade almost has gone by. In this decade, we haven't yet, I believe, put the topic to rest. We don't know exactly why it is so easy to attack neural networks. Or there are ways to attack neural networks. People have different hypotheses. But we have learned a lot along the way. And I'm going to focus on what we learned after we walked through this paper. When you look back in retrospect at these ideas, this is Ian Goodfellow, one of the leaders in this field, in fact, and the author of the textbook, Deep Learning, co-author of the talk. Obviously, he is as good as it gets. Now, he says that the problems have to do with the fact that with the activation function and with the fact that it's too linear. The problem is neural networks are too simple, and the decision boundaries they build, they are piecewise linear in effect. Right? And that is the problem. Today, then another school of thought came about that argued the other way around. They said, oh, neural networks are so easy to attack because they are too nonlinear. And there are many, many ideas that came out that try to explain why you can do an adversarial attack on neural networks. I'm going to cover in the second paper that I read, perhaps one of the most plausible theories that have emerged. It is called the dimple manifold theory. And another related to it is, closely related, is the manifold curvature theory, that at those places where the manifold has strong curvature, you tend to have more potential for adversarial examples. So both of these are beautiful geometric ideas, which is why I like them. And I tend to believe that they are close to the right answer if they are not the right answer. They're very close to the right answer. Albert?
Yes, so I went to the AI conference, right? So they have security over your models. They have this layer to protect all your models from these attacks.
And how do they do that?
I don't know. We have all these companies that come out to handle that. And that was interesting.
Yes.
I don't know how they should. I didn't focus on that.
Yeah.
Now that you say it,
Yes.
I was
yes,
thinking, how could they attack a model? Now that this thing, now
it's too easy. It's
Yeah.
just too easy.
That's what
But you can see their attacks and their defenses. And where we are is that if we think this is a vector of attack, we have a few approaches to defend, and we'll talk about those approaches, but it's a cat and mouse game at this moment. Right? So this paper, remember that this is an old paper, right? And some of the things that it says at that time, and this is why a brilliant thinking is very well thought out. Nonetheless, it is today, I don't think we quite agree or fully agree with the things that it says. And that's the nature of research. You keep hoping that you are proven wrong, right? Because what is worse than being proven wrong? Not proven right. Is not to be noticed at all. Your idea, most papers are not noticed at all. Most researchers, they toil away in relative obscurity, and their works are never. I mean, they get thrilled if somebody even criticizes the work, because it means somebody looked at it. But obviously, Ian Goodfellow is one of the greatest, and his ideas are obviously pretty deep and well thought out. And this way that he explains is genuinely very nice. So this paper is made up of brilliant ideas, some of which have survived the test of time, some of which we are not so sure about anymore. So with those caveats, let us begin. Okay. So I'm saying that just so that you don't believe, like when you read this paper later on again on your own, review it, you don't have the conception that everything that is here is what we think it is. So if I look at this paper, it says several machine learning models, including neural networks, consistently misclassify adversarial examples. So we know that this happens. By the way, this is not just true of neural networks. You can take anything. You can start with linear or logistic regression, and you can do that. Right? Those of you, I mean, just somewhat related. If you remember, even with very basic ML100s, the linear regression that we learned, we used to worry about points of high leverage. Do you remember? Those points that are hiding in there, but their value has undue influence. And if you remove those points, then the model changes. And they're not even visible. Outliers are visible. Outliers have an impact on a linear model, but you can see them. These points of high leverage are hiding in there. And so you use all these techniques, Cook's distance and this and that, to ferret them out. So then, but you can do with logistic regression, with all of these things, you can easily cook up things. Support vector machines can be poisoned. So all of these models are susceptible to problems. And what it says is, several machine learning models, including neural networks, consistently misclassify adversarial example. Inputs formed by applying small but intentionally worst case perturbations to examples from the dataset, such that the perturbed input results in the model outputting an incorrect answer with high confidence. And if you see that the approach that these authors are saying, it is not necessarily specific to neural networks. It says, given a loss function and given a classifier that builds a decision boundary, you can use this method to quickly create adversarial examples and basically to attack models. Are we together? So how would you do that? The one thing that you need access to in this particular case is the loss function. You have to see how the loss function changes or doesn't change, right? But what you do is, and this is the gist of this, is this. See, you take an input. This box is there. This is your model. Right? Now, and pay attention to the main idea, is very simple. Suppose I have X going in. What does a classifier produce? Y hat, which is the probability of something. Let's say probability of a panda, isn't it? Or more strictly, it is probability of a class, some label, given X. Strictly speaking, this is what it produces. And then you apply a threshold, you say, if it is the highest probability, then this is the guy, or something like that, or more than 50, or whatever it is, all of those, and then you come up with a prediction. But this is the important thing, it produces a probability. Most models. So far, so good, guys. Are you seeing my screen? Yeah. So now, and this is what it is. Out of the probability, you create a cost function, a loss function. I think they use L or J. I consistently use L. So forgive me if I, what do they use? Related work, J. But my L and the J is the same in this paper. Equivalent to J, loss function. And people sometimes use the word cost function. These days, loss function has become more or less the word most people use. So now I'll ask this. Would you agree that if I make a perturbation to X prime, I just make a small perturbation, shake up the value of X a little bit randomly, or what will it do to Y hat? It will produce, hopefully, a slightly different prediction, isn't it? The probability of that class, let's say panda, might change a little bit, right? So what will happen is, it will lead to Y hat prime is equal to Y hat plus delta Y hat. Now, intuitively, this is a vector. Obviously, these are vectors because this input is a vector. What do I need to do? Delta Y hat is, of course, just a number. It's a probability change. Now, delta X, given X, it could be any one of the directions, right? And if you are in a 100-dimensional space or 1,000-dimensional space, there are infinitely many things that you can do. Now, the only question is, if you happen to choose a direction in which I could decrease the probability of a panda or probability of the class, I can find which direction do I need to move. Pay attention to it. Which direction I need to move such that my move is just tiny, but the response change is high. Loss function change is high. Are we together? So this will lead to change in a delta loss function is equal to L plus delta L, right? So you want to maximize the loss function. But in which direction given, so loss function is a function, right? It is a function. It's a function of, at this particular moment, X and theta, L. Suppose the weights of the model you can't change because you're doing adversarial attack. You're not allowed, you don't have access to the weights. So the only thing you can change is X, the weights and biases, which I represent in this paper as theta, right? You can't change those, but you can change the weight, change X. What is the direction of maximum change of X? Of L, sorry. What is the direction? If I have a function of X, in which direction do I need to go to get the maximum change in that function? Remember this thing, this inverted pyramid. What was that? Gradient. That's the whole idea of gradient descent, isn't it? So when you take the gradient of a function, gradient of L with respect to X, of course, implicitly, it will point in the direction that if you go that way, my loss will increase the most. Did you see that? And then what you do is, what do you do in gradient ascent, gradient descent? You make a tiny step. You don't just go hello, just make a tiny little step in that direction, right? Because this gradient may be very steep. You don't want to take such a big step. You take a tiny step. What's the typical learning rate people use? 0.001, 0.0001 or something. You make a tiny thing. Then again evaluate, iterate back to it. Which direction should I go? For each point in my input, in this picture, so how do I change the picture? How do I change this vector? Right? Such that changing this picture, this 768 dimensional picture, let's say, right, with this pixel value, which direction should I go? That direction would be, you're basically saying that the x prime should be equal to x plus a tiny amount in the direction that is going to most confuse the loss function. Are we together? The model, because the loss function change would be the maximum. Now think about it. You want the probability to increase or decrease? Decrease, right? So you just want to make sure that if it is saying cat, it should suddenly start saying dog without making too much change. And that is the gist of the idea. Now, one more thing they do is that, see, this will be a quantity, right? To sort of normalize it and make sure things happen in a disciplined way, they don't take the whole of it, they just take the sign of it. +1, -1. They just want the direction, not the magnitude of the gradient. Right? In gradient descent, you care for the magnitude also. So this becomes x prime is equal to epsilon sine of gradient of the loss. Does it make sense, guys? Does it make total sense? So x is equal to, or you can say delta x, the change that you make is equal to some tiny amount of that direction. So far, so good, guys? Right.
That's why it's called fast time.
Yes. That is it, and that is all there is to this algorithm. Okay. So
Asif, you are reducing the loss function or increasing the loss function?
you are doing it in such a way, and so let's do that. See, let us read this paragraph. The linear view of adversarial examples suggests a fast way of generating them. We hypothesize that neural networks are too linear to resist linear adversarial perturbation. This, by the way, even if you don't make this hypothesis, this method still works, right? So, so there we go. Too linear to resist linear. LSTMs, blah, 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 and max out are all intentionally designed to behave very linearly so that they're easier to optimize. You can ignore that. Morely, such as sigmoid networks are carefully tuned to spend most of their time in non-saturated, more linear regions of the same. This linear behavior suggests that cheap analytical perturbation. So he's saying that whether you use sigmoids, the non-linear activations, or explicitly linear activations, small changes are always linear effects, right? That's all he's saying. This linear behavior is a cheap analytical perturbation of a linear model should damage. You see, the idea was literally that, basic calculus. Let theta be the parameters of the model, x be the, so what are the parameters of a neural network? Weights and biases. X is the input. In this particular case, what is x? X could be literally the image vector, right? And or it could be the tensor, whatever it is, but yeah, let's take it this way. The target associated with x, the learning task, and j be the cost function. So the only difference is here, my L is j, is equivalent to j. The cost is j. We can linearize the cost function around the current value of theta, obtaining a max norm constraint perturbation. So now, this is the perturbation. This is the delta x kind of thing. Right? Epsilon, the sign of the gradient. We refer to this method as fast gradient sign method.
What is the theta again?
Just the weights and biases.
But how do you know the
But
weights and biases?
you don't need to. That's the whole point. Because you're doing gradient with respect to input.
Yeah, but why does the, okay, the loss function has,
Yeah, it is built in. It just has that built in.
but you don't.
But you are
have-
not changing that.
Yeah.
You're taking the gradient. If you look at that, below the gradient, the subscript is x. See what in reality, think about it. In reality, if you want to, I want to attack your model. Do I know your weights and biases? I don't. But what do I know? I know my inputs. Right now, if only I can see your output or somehow get a sense of the cost function. Now, suppose it's producing probability. Oh, good heavens. Now everything is easy. I do a little bit of calculus, bring in my cross entropy loss function, do a bit of calculus and say, okay, I know the derivative. Now I can start doing my perturbations of the input that will create, I can quickly calculate the gradient of the loss. And therefore I can attack this box.
So as your input then would be the merging of the two. So
Yeah. So what you do is your input. So this thing. So see my delta x, what I call delta x, and so your new input will be x prime. This is it. Plus, let me write in. See, basically what we are saying is plus. This is what we are saying, isn't it? So you take what plus x plus x, the previous picture, take the picture of the panda and add this. But when you look at it on each of the axes, which is actually each of the pixels, there will be some tiny little bit of perturbation. When you try to visualize that perturbation as a picture, because this itself is a vector, this is a vector. When you devector, when you square it or rectangle it, and you see what does it look like, right? It will look like noise, right? It will look like this noise. This is literally the matrix. That is it. So you see them doing that. Your x is the image. This is your epsilon, tiny bit, 0.007, right? And this is this pixel map noise is literally the sign of this thing. Now, why did he take 0.007 learning rate? He was just, I think a little bit of it is just experimentation, but he goes on to say that it corresponds to, like, you want to just stay below the perception level, right? Equal to gradient of the cost functions. Here, to the magnitude of the smallest bit of an 8 image encoded. So it's taking implementation. He's looking at that 8-bit image and he's saying, okay, when you convert it to real numbers, then just this is about as tiny a step as you can take. Right. So he's taking very tiny steps. Any tinier than that, and it won't show up as change at all. Yeah, go ahead.
I'm thinking aloud here, and maybe I'm wrong. A lot of so identity goes, you need to take a picture, you have to upload a picture, right? Let's say for my passport, you uploaded a picture. Can I upload a picture with some little modification to it, like a little noise, and make sure it does not match the person? Is that
Yeah, of course, totally. Yeah.
And point it to somebody else. Exactly.
Yeah.
Should that be a real life example of this?
Yeah, of course. Yeah. 1 second. So the idea is that I'm a person. If I want to confuse this system, let's say that in front of the building, here's a system that does people identification. Yeah. Right? So it is looking at the camera. If somewhere I could insert between the camera and the AI system, somehow I have a way of injecting noise, right?
Why aren't we seeing more of this?
Because in this, there is one thing that you need to have. This is the easiest method, but here the weakness of this is you need to have access to the probabilities that it's producing. So it's a little bit more closed box, but there are more attacks as we learn about it that are doing. See, today models are being attacked all the time. You should just assume that, is adversarial attacks happening? They are beginning to attack. It's like a curve. Let's just say that not many people have heard of the topic of adversarial attacks, right? It's still a small world, but that world is pretty active. AI comes with great security concerns.
So I'm confused. How will you attack the model? Right? What do you mean attack the model?
You make wrong predictions.
No, that I understand, but the model is hidden behind your code, right? So
See,
Your-
your
your
model,
software.
see, here's the thing. Suppose your model may be hidden behind the code, but suppose in the API or your UI or something, I also emit out the probability of this. I emit out this number. Then what do? I just start making tiny little changes and figuring out which way I need to go.
No, we technically get this in ARAG. ARAG isn't possible without this.
Exactly this. See, guys, machine learning, right? The whole of learning it's a bit of an exaggeration, but a large part of learning comes from this particular symbol, right? The gradient is the guide to everything, to optimizing, to learning, to, you see this here, the attacker is learning how to attack. Right? This is it. And so this equation, guys, now does it make obvious sense? It's a very obvious equation. If I could see the probabilities and I could see the loss, therefore I can do the loss gradient, I am done. I can create a pixel map of noise that may be sub-perception. When you add it to these pictures, there is no way you can tell it apart. Right? The first time I read this paper, I said, are you sure that they just didn't accidentally copy paste the same thing twice? Because the more you stare at it, the more you realize that actually there is no difference. There is difference, but you can't make out of it. So this is it. You have adversarial attack. Now, the explanation that is given, I would not read the rest of the paper at this moment, because today we don't think like that.
But Asif, I agree with Albert's point here. See, you have a model that's sitting somewhere on your GPU, right? Either you're doing like reinforced learning on it or something where you're even giving me a way to give you bad input to modify it, right? So if I'm able to give you a second image like that,
Yeah.
which has the disturbances in it,
Hmm.
only then you can, and you're actually learning from it,
Yeah,
only then this attack is possible. Right?
exactly. So the underline is, that's why it's the simplest. See, this is an academic paper. It shows the possibilities.
I see.
Once a possibilities are revealed, now you have to think, like, so take on the persona of the attacker. Now you have to think, okay, how do I go about it? Oh, here is an API. It's telling me the probability. And by the way, there is no restriction on how many inputs I can keep submitting to it. Right. So then I can theoretically soon construct an input where a pandas looks like a given to the machine, and then I can write a little blog. This algorithm is totally wrong. See, it is calling this a panda.
So Satyam, say suppose I join a company and I'm a row, I can add that particular inmate into the model.
You're talking about an insider attack.
Yes, but it's an
Yeah.
attack, right? So
Yeah.
it's vulnerable. So there could be any type of attack.
So my point is that the work you could do, you're on the inside, you could destroy the whole thing. Why do you, like, what fun are you getting by tweaking a model?
Getting this to be part of the
If
attack
I'm
vector is
intelligent,
probably a stretch.
You won't be able to figure it out.
Yeah, see, this is the
If
one
I
of
just
the
pull the box down,
simplest
then you can catch
attack
something.
forms, but people have used this. People have used this. Huh?
But it's
Uh,
not
ask,
easy for a
I think Sanjay is waiting for code sometime. Go ahead.
Asif, you can comment, explain the statement of the regularization techniques not being effective in reducing.
In the introduction where it says, say the sentence, which page?
The generic regularization.
No, paragraph number and line.
The second paragraph, last
Yeah,
sentence.
it's the second paragraph.
The
Last-
generic regularization strategies such as dropout, pre-training, and model averaging do not confer a significant reduction in the model's vulnerability to error, but changing to nonlinear model families such as RBFs can do so. So what he's pointing out, which is true, that obviously you must have noticed it's true, that dropout won't help you. Right?
I mean, just not drop out.
Multiple regularization techniques. Actually, today, we are not so sure of that statement, actually. The next paper, which is much more recent, you'll realize that as disciplined regularization, a smoothing of the manifold, regularization geometrically shows up as a smoothing of the manifold or straightening it out a little bit. Yeah. So there are certain forms of regularization which do help.
Asif,
Yes.
is there a way to freeze the inference model parameters all the time?
Is there a way to freeze? No, they are always frozen. Remember, theta is not being changed in this attack, right? People are playing with the input and they're trying to see which input will fool the model.
Okay.
That is it. So here's an example. Suppose your boss has access to something precious. Let's say that office room behind which all the good cookies are, but you don't. And outside that door, there is a facial recognizer. And you say, damn, now all you need to do is, your boss isn't there. You take a picture of yourself or somebody who's somewhat close enough to the boss, and you start making tiny changes to the boss's picture and keep showing it to the facial recognition system. I mean, to that picture that you started with, any picture, maybe it's a picture of a monkey. You start making tiny perturbations to the monkey and you see gradually, can it fool the recognition system into the belief that it's the boss? Because what is your goal? To somehow make it infer it's the boss and you go get the cookies. So that's how you would look at it.
Got it.
Yeah,
So
but
you keep making changes until it looks like a boss.
until it looks like a boss. And then you paste a picture of that monkey all over the wall and say boss.
But as you're gradually increasing the loss, it's just not being able to predict it as you, right?
Come again?
Because if you're adding more noise to your face, it's just making it more and more likely not to predict you, right?
That is right.
How do you
That
get
is
to
right.
make it
So what
predict
happens
the
is,
boss?
generally what happens is, and this is the funny thing, with these complex networks, generally, like you can start with let's say that more realistically, you started with somebody who sort of has a facial structure similar to the boss, and you start making tiny perturbations. If you can see the probability, like suppose that facial recognition very helpfully has given you probability allowed, probability of a boss 99% or something like that, right? Or 10 not allowed 10%. And then you make a tiny perturbation, say, 10 point probability of boss, still not allowed, probability of boss 10.01%. You say, aha, I'm onto something. And you keep making tiny perturbations. And surprising thing is, you would imagine, so I'll come to that. I know somebody is waiting. You would imagine that by the time you hack that machine, the thing doesn't look like either the first person or the
UPS.
right. But in reality, what happens is it more or less looks like the original guy, because the perturbations needed are so small and subtle that people would not even know that an adversarial attack is. All they will know is somehow Patrick was misinterpreted as the boss, and now Patrick has all the cookies. Right? That's all.
But content example is exactly that.
Exactly. That.
Yes.
खुला जा सकता है अभी
Within
इधर बात जाता है
non-human
ब्रेक हो ना
world, for example, can you corrupt the data in a way that, let's say, it can influence somebody's credit score?
Yeah. So what happens is that that's the risk, and this field has exploded. The simple answer is yes, potentially. You just have to find specific avenues for making things happen, and you have to hope that those people who maintain credit scores are a bunch of Equifax geniuses. Right?
Are the dimensions for text lesser than images as a
Come again? No. Easily reworded. So, for example, I write a text, you classify it as a positive sentiment. I can just turn a little word and then it will suddenly say negative, but I'm still saying the same. Right. So the perturbations would be just making synonymous change, synonyms or something. And you're making very slight change perturbations in the semantics of it. If you think in terms of vector embedding, right? Think about it as vector embedding. That vector is at that point is just drifting a little bit. It just is finding where is the decision boundary, and it needs to just cross over a little bit. The nearest distance to the decision boundary and just cross over. That's all it's trying to do. You see that, right? Right. That's it. And so you try to start with an example. So here is the trick part of it. there is an interesting thing. You would say that, hey, if it is a perfectly good picture, sometimes you are far from the decision boundary, right? Which is true. And so I was hoping one of you would notice that actually the machine was not very confident that it's a panda. You want to pick cases like that first. You want to pick, do you notice that? Right? So in a way you can say, well, it's plausible because this is already not a very confident answer that's a panda. And then you pushed it over the threshold. Isn't it? But what is interesting is, what is it calling the noise? It's calling the noise a worm, right? Nematodes. So it sees this, and actually I stared at it quite hard to see where the worm is, but I couldn't make out. So, okay, guys, so that's that. Was it fun with this paper? This is it.
Yeah, there's something called text attack.
Yeah.
Python library. Are you familiar with that?
Oh, there are many libraries. I don't think I've heard it. I've not used it for sure, but at one time I was researching all these libraries and methods of attack. So it may have come up in the list, but I've not actively
So
used it.
so my second question is, similar attacks can be done against text or images.
Text or images or anything, or music, audio. I can.
How do we protect against it?
Oh, so that brings us to the defenses.
Yes.
Defenses. Okay, so for that, part of the answer I'll introduce now, and the rest of the answer, unfortunately, I won't give because it's a long discussion. And when I do fraud and anomaly detection, it is actually part of that course. Okay? So it's a big topic, like there's too much there. But in a way, I'll start to answer that question in the next paper.
Okay.
And at the same time, I would strongly encourage you to read the reference. See, the reference is there. You don't have to wait for me to give that course. In the references, I've given that to you. Let's go back to, see, after this, the next slide, you see that defenses. A survey of adversarial attacks and defenses. You see that, right? So just click on that paper. I mean, there are many such papers that are survey papers. This is one of them, or survey articles. This is one of them. I believe this came out in IEEE or something like that. Yeah. So it's a big field, guys. Adversarial attacks and defenses is a big field. And many people are completely dedicated to it. Now, it is important for you to know about it, which is why I'm introducing it to you. And some of it I also do as part of fraud and anomaly detection, because these can be used for malicious intentions. And but broadly speaking, I don't like, if I were to go in depth into it, it would be a workshop of itself. All right, guys, so we meet again. Are you in a mood for the next paper, or are you done?
No, we are.
But have you, please read it. This time I went around asking what is the algo, and I didn't quite get very crisp answers. So actually read the next paper. It's a beautiful paper. To me, as a person who loves manifolds, geometry, etc., topology, it's a very, very beautifully argued paper. Read it. I'll catch up with you in half an hour.
So also for this, well, does this mean that, using our LLM agents and all that, are they're also prone to this kind of
Everything.
So we could essentially disable a whole agent pipeline just by an adversarial attack.
Yes, you can. It is. Like at this moment, right? This is the danger that people don't realize with AI, of how susceptible. See, our training place is called support vectors. It's a pretty clever algorithm. And then one day I realized to my disappointment a paper or a discussion that showed that you can very easily poison support vector machines. So complex algorithms are easy to poison. And even simple algorithms are easy to poison, by the way, nothing complex. This is a point Goodfellow makes, is that even linear regression, I mean, you can poison anything.
So just like all these classification algorithms we're talking about, how they identify a cow and a duck, right? Because of the beak or because of the weight. So these are kind of, in that cases, the model is quite weak in the sense it has few features, and if somebody modifies that a little bit, then a duck can become a cow, and a cow can, and that's probably it when you add the noise. There
Yeah.
are commonality that
No, the way I would say, Albert, is it's not weak. It's just that making the decision is complex, and because it builds the decision boundary that it builds. Actually, the real reason nobody really knows, but the best hypothesis is the decision boundary that it makes is unstable. Like it is not with small, like it is such, and that's exactly the context of the next paper, which is the dimpled manifold hypothesis, that inherently it ends up leaving patches where it is easy to create adversarial examples, regions of the feature space where you can easily create, and not only one, quite a few examples, adversarial examples. So initially the hope was that you could localize all the adversarial examples to one region of the feature space, and then you could just blacklist any input coming from that region. But that hope didn't work out. Right? So that simple blacklisting kind of argument, and now we know that adversarial examples are quite widespread. And the next, which is why, see guys, you're asking all the right questions. It should make you study the next paper with great care. And I can see that actually you guys haven't studied it. So how about this? I'll give, instead of half an hour, I'll give you guys 1 hour. Take a whole hour, but study the paper. Right? Please get back into your rooms. Don't code. Don't do your implementations. Read this paper. It will take you half an hour. After that, you can start coding. We'll take it from there.
What are the advice methods against this attacks?
Oh, it's a pretty big topic, but broadly, there are many ways of dealing with it. Some of which we'll cover in the next paper, but broadly many things. So, for example, you deliberately give it adversarial examples. You create it, and then you make it part of the training data. And you say, this is a panda, not a. So then what happens is the hope is that the decision boundary will shift and stabilize. Does it actually really work perfectly? Partially works. That makes it better. And in fact, most of the companies that you're talking about, Albert, my guess is that they are into some, see, this topic is very fresh. Most people don't even know the easy solutions like this, right? So
I was just wondering, like, the change our mind, right? What if we just resize it by like 10%? Would that affect the final result? Because, like,
resize means?
Like you get a 1000 by 1000 image, you convert it into 900 by 900. So wouldn't, like, because it's getting resized, wouldn't these pixels be kind of like, merged and, like the end result image, wouldn't it have a different effect on the model?
No, you're asking that in a way, if I change the picture and its dimensionality itself, every model takes a picture of one dimension, pick a dimension, whatever it is, 1000 dimension, or I mean, let's say that if you take 1000 by 1000 pixel, you're looking at a million dimension. But you convolute on it, so it's never really that heavy, but it's still a very high dimensional picture. The moment you do any reduction, size reduction, yes, you're right. Every size reduction implies pixel merging of some form, right? And there is a loss. There is a loss of information, but you usually don't call it an adversarial attack. It is just, it's been a part of.
I mean, can we use that against attacks? Because, like, the pixels got merged. Now, whatever
No,
the
you
attacker
can't,
was using,
because it is a property of the decision boundary. It's a property of the way this neural net, all the AI machine learning models work. It's a property of the decision boundary. You can give me any data. You think about this method. Nowhere does it say what the dimensionality of the vector should be, right? Whereas the size of the picture, it only speaks to the dimensionality of the input. So invariant of the dimensionality of the input, you can still apply this. And a whole class of other methods. This is one of the simplest ones.
But to Srinath's point, if I got that panda with noise image, and then I resize that. That doesn't necessarily mean it's gonna trigger a headline. I essentially have to resample the noise. but
You
for
need
this
to do
one-
adversarial injection. Just resizing is not going to make the thing look. And in more practically speaking, there's models, they take a one given dimensionality. So resizing anyway won't help, because if it takes a million pixel input, you can't give it a resized image, because you'll have to again blow it up. So that's a very practical impediment.
So it was an image that you resize, it will still stay poison.
Yeah. Yeah,
So if I look at it, this problem, right, we assume our eye and human brain, right? You assume that is a neural network. That is in the question. It's an essence. To our eyes, the panda and the panda plus noise will be exactly the same. You're not
Yes.
able to see the difference.
Mhm.
So is the root of the problem is because you have too many bits to represent something. You are basically looking at all the noise. Instead, you look at the essence of it.
no. It's the opposite. It is the fact that the human perception. See, you can theoretically assume that the middle picture in the paper, where is it? I have to go to the paper now. Give me 1 second. Where was I? Oh, did I close it? I might have accidentally closed it. Okay. So the panda plus noise, to our human eye, it is not sensitive enough to know the distinction. So the attack was done by injecting a sub-threshold noise. There's a threshold of perception and deliberation. So you could say that if I was a green Martian alien with much better perception, static perception, I may have noticed it. Yeah.
So I'm just assuming like there is some bit precision. If I assume my eye as a camera, it looks like our eye as well. Fewer bits.
Possibly our high is not, I don't know how to answer that. I'm not an expert, but see, especially you're looking at it from a picture
Take the
perspective.
same image and assign lesser bits for the pixels. Then your neural network solution also will be more robust.
No, it doesn't solve that. I'm telling you that the input dimensionality makes no difference. This method can be applied. Remember, it's the gradient on the input.
So
Not the dimensionality.
wherever you're getting into the shady zone or not so confident zone, that's where you can bias the decision.
The basically like a wireless. Absolutely a wireless for. Yeah. Because.
No, I actually have a very practical problem. See, I mean, everybody's